Good afternoon, everyone. I'm the first author of this paper. Today, I'm going to give a presentation of a deep learning method for ASD identification named Skill Adaptive Graph Convolutional Network. My talk includes 3 parts. To begin with, I'd like to introduce Autism Spectrum Disorder, ASD. What is ASD and how to diagnose it? Autism is a neurodevelopmental disability which starts in early childhood and affects how the brain grows and functions. And it is always characterized by stereotyped behavior, language disability, difficulties with social interaction, and so on. Some researchers have found that autistic individuals show insufficient or excessive connectivity between certain brain regions, like amygdala and hippocampus. Therefore, functional magnetic resonance imaging technology is beginning to be used to diagnose autism because it can record brain activity and capture abnormal functional connections. Until now, many deep learning methods based on fMRI data have been proposed. The most effective method is the graph convolutional network based on the population graph, which is constructed with multimodal data, the imaging data, and the phenotypic data. In the population graph, each node represents a sample, and the attributes are determined by the similarity between them. After that, the node features are aggregated through the graph convolutional network. This framework was first proposed in 2018. Subsequently, many studies adopted this framework and made some improvements. Among them, the GCN was proposed with an adaptive population graph construction method named Pairwise Association Encoder (PAE), and the Deep GCN was designed as a 16-layer deep graph convolutional network. Based on the advantages of this framework, our method also adopted it. Then I will introduce our method as a GCN in detail, Skill Adaptive Graph Convolutional Network. In our method, we propose some solutions to solve the problems existing in the previous studies. In prior methods, they only use one brain atlas to partition the whole brain to gather brain functional connectivity, but it ignores the complementary information between different brain atlases. Thus, in our study, we adopt mutual learning between different atlases to integrate multi-skill spatial information contained in them. Furthermore, to better learn the information contained in the graph, multiple graph convolutional layers have been stacked in the network, which may result in over-smoothing problem. To solve this, we add the attention-based jumping connections in our graph convolutional network to reduce information loss of previous layers. This is the overall framework of our method. It contains 4 main components: data pre-processing, population graph construction, feature learning through GCN, and mutual learning between different atlases. First, we have to pre-process the raw fMRI data and the phenotypic data. And for the fMRI data, we adopt a widely used pre-processing pipeline, CPAC. And for each subject, we can get a 2,000-dimensional fMRI features. And then we normalize the phenotypic data to obtain the phenotypic features. After that, we have to construct 2 kinds of population graphs for the GCN, the feature graph and the topology graph. For both of them, the graph nodes are represented by the fMRI features, but the edges are constructed in different ways. For the feature graph, the edges are constructed by calculating the correlation distance between the fMRI features of different subjects. And the edges in the topology graph are represented by the cosine similarity of phenotypic data. In our study, we choose 2 kinds of phenotypic data, the acquisition site and gender. Then we feed these 2 graphs into our GCN, the Adaptive Multi-Channel Graph Convolutional Network. It consists of 3 channels, 2 specific channels and a common one. The specific channels aim to learn the specific features from these 2 graphs respectively, and the common one can capture the shared information of these two graphs. The structures in these three channels are identical, which includes an edge dropout layer followed by a series of check-shaped graph convolution layers with attention-based jumping connections, a fusion layer for feature fusing, and a multi-layer perceptron for node prediction. The edge drop layer aims to increase the sparsity of the graph and reduce overfitting. The edge dropout layer aims to increase the sparsity of the graph and reduce overfitting by randomly deleting parts of the edges during training. After that, we get three different embeddings, two specific embeddings HF and HT, and a common embedding HC. Finally, we feed them into an attention module to obtain the final embedding. And in our method, we designed two parallel AM GCNs for two different brain atlases for mutual learning. It is Harvard-Oxford Brain Atlas and Cracked-Up 200 Atlas. The loss function in our network is consisted of two parts, the supervised loss and the mimicry loss. The supervised loss is defined as the cross entropy between the predicted values and the ground truth. And since the main purpose of mutual learning is to make the predictions of different networks based on the different brain atlases as consistent as possible, we adopt the mimicry loss in the training phase to calculate the difference between them. It was represented by the Kullback-Leibler divergence of posterior probabilities from these two different networks. Thus, in the training phase, these two parallel networks can share training experiences with each other. The last part is experiments and results. We verify our method on the dataset ABIDE. ABIDE is collected from laboratories around the world to accelerate autism study. It includes two large-scale collections, ABIDE 1 and ABIDE 2, and we verify our method on ABIDE 1. It was collected from 17 different acquisition sites and it contains 1,112 subjects in total. But for a consistent comparison, we select the same 871 subjects, including 403 individuals with ASD and 468 typical controls. The table at the bottom shows the demographic information of the subjects. By comparing our method with others, we can see that our method achieves state-of-the-art classification accuracy on ABIDE 1. Furthermore, we conduct some ablation studies to verify the effectiveness of our proposed attention-based jumping connections and the mutual learning strategy. First, we investigate the effects of the attention-based jumping connections by comparing it with three different methods: without jumping connections with vertex-wise concatenation used in EVGCN, and mean jumping connections, which assigns the same weight to each layer. Meanwhile, we verify the effectiveness of the mutual learning through using only Cracked-Up 200 Atlas or Harvard-Oxford Atlas or their combination. Obviously, the results didn't disappoint. Finally, to evaluate the capability of the SAGCN more intuitively, we visualize the original features and the learned node embeddings through T-distributed stochastic neighbor embedding in two-dimensional space. Look at these two figures. We can find that the features of autistic individuals and typical controls in Figure A are close to each other and overlap, which shows the difficulty of ASD classification based on fMRI data. In contrast to Figure A, the node embeddings learned by SAGCN are well separated in Figure B. The samples with the same label are clustered together and have clear boundaries with the other group, which means that the node embeddings learned by SAGCN can precisely represent the intra-class similarity and capture the inter-class differences. And it proves the effectiveness of our proposed SAGCN once again. Okay, that's all my presentation of our study. And this is our research team. Our research mainly focuses on the computer-aided diagnosis of autism and depression. This is our publications in recent years. If you are interested in our research, welcome to read these articles to learn more. Thank you.